Hello, and welcome to the Industrial Innovators Podcast, hosted by founder and CEO of Innovator, Don Cooper. I am Wyatt McPherson. I produce this show, and today our guest is Matt Rybicki from ForgeTech, and he and Don will be discussing a brand new technology now offered by Innovator, known as friction forge bonding. So let's hear what they have to say.
All right, so today we're here with Matt Rybicki from ForgeTech, and we're going to introduce our audience to a new technology called forge bonding. So, Matt, welcome.
Thank you. Appreciate you having me here.
Why don't you tell us, who's ForgeTech?
Well, ForgeTech is an industrial technology company. And we have a technology for joining metals without any sparks or flames. It allows us to go into chemical plants and refineries and perform work without being a hazard. We've been around since 2010. We incorporated that year. It was the year that our first patent issued. And we've got 18 patents now that have issued, some foreign, some US. And we continue to build our patent portfolio, and we continue to refine our technology. So we've been around quite a few years. The technology was actually invented before we incorporated back in the early 2000s. And the inventor of the technology still works for our company and continues to move the technology forward.
And now, who was that? Have I met him?
Mike Miller. Yes, he was
Okay,
actually.
Yeah. Great. Yeah, that's Mike. Mike was up with our team training us just a few weeks ago. That's great. Yeah, I thought that Mike had a lot to do with inventing the technology. So your business has been, incorporated as a business with patents since 2009. But this was a technology that was developing long before that with Mike. Is that right?
That's right. He was actually developing it in his garage over a decade or two.
Right.
Mike actually started in the leak sealing industry, and he used to be up on tank roofs, drilling and tapping to put plates down and stop leaks, and trying to repair valves with drill and tap. And he realized there's got to be a better way. So he, in his after hours and weekends, he slowly developed the technology through funding of his father in his garage. And as the technology came to fruition and became where he felt it was comfortable bringing it to the market, the company took in a round of funding in 2010. And I joined the board of directors at that time. And we continued to develop the technology and build the market since then.
Awesome. So the technology we're talking about in aggregate is something called friction bonding, right?
Well, we term it forge bonding, and that's our marketing term.
Forge bonding, right. Sorry, I confuse those two terminologies between friction forge bonding and forge bonding. So you call it in the marketplace forge bonding. Okay.
Yes, we have actually evolved our marketing term for what the process is. And actually, it's actually evolved from a technology called friction welding that's been around since the 1950s. And it's actually currently used in manufacturing today. Friction welding is. It's used in automotive and aerospace industries and many others. But when it's used in manufacturing, it's usually a large floor standing piece of equipment. It can be used in a manufacturing facility. It's not portable. It can't be. You have to bring the work to the forge bonding machine rather than the forge bonding machine to the client.
Right. So you've taken some large stationary technology and made it portable, so you could take it into process facilities and then use a variety of applications that you've developed with that portable technology, right?
That's right. There's actually two changes or improvements we made to friction welding. Number one is we did make it portable, like you said, so that we could bring it into the facilities where the work needs to be done. Secondly, we minimize the thermal energy required to join the two metals together. And so we term it forge bonding because we're never reaching the molten temperatures that typical welding processes use. We're only bringing the metal to a forging temperature, and under pressure and rotation, we drive those two metals together.
Okay. So just describe in as many words as you need for anyone who's listening exactly what forge bonding is. Then what is it in the most layman terms in terms of what you're doing.
Okay. Well, we take a 5/16" stud. I think you can probably see that okay here. Stainless steel stud, and we apply a pressure to it, and then we rotate it for a few seconds. And after that rotation and pressure, we end up with a stud bonded to a piece of steel like this, and it's a permanent bond. It takes the actual bond is actually stronger than either of the two metals that are involved in the process, and we can bond different types of metals and materials. But it's basically pressure and rotation that drives the two metals together. Happens in about 3 seconds. We've qualified quite a few different metals for forged bonding. Some are stainless steel, some are carbon steels, and customers bring us regularly different metals that we need to qualify before we actually perform work.
So the forge bonding process is, for all of us Boy Scouts out there, it's like when we took the one stick and spun it really fast against the wood to create some friction to create a fire, except we're doing this with high strength materials, stainless and carbon steel.
That's a good analogy. Under that pressure and rotation, there's a small amount of thermal energy that's generated at that interface where the rotation is occurring. And it does soften the two metals to a clay-like consistency. And under the pressure and that rotation, those two metals get driven together. That's
awesome.
All in a nutshell.
Okay, so what are the customer applications and the economic conditions that are best suited for forged bonding? Then, like, where is a customer best going to be able to utilize this and get value from it?
Right. So that's a good question, and it's really where our value comes in. Our technology is best suited for situations where you can't get a hot work permit. That's number one, because welding is an alternative if you can get a hot work permit. But what our value is we can come into a hazardous or flammable environment and perform retrofits or repairs without creating an ignition source. So the other situation that's very well suited for forged bonding is if you have a tank with a liner on it, for instance, or you have a pipe that has been heat treated. The amount of thermal energy we generate is not enough to destroy the liner on that tank or to take the heat treating out of the piping.
Okay.
So there's a number of advantages. Also, we have a number of customers who would like to install, who are trying to upgrade the safety in their facilities, like install handrails or fall protection or fire suppression, foam injection nozzles, and they can't do it unless they take their units, their process lines down. And so we can perform work while their process lines remain up and running.
Right. Okay. So, the kinds of applications that you're seeing traditionally, you're repairing tanks, large storage tanks, tank roofs, sidewall corrosion issues. You're also doing a variety of handrails and other structural fixtures in both in tank farms and in process facilities.
That's right. We work in refineries and then midstream terminals, tank farms, like you said. Those are the two primary areas. We've done quite a bit of work in chemical plants. In fact, we have a big job starting next week to install handrails in a second chemical plant. And we've done a little bit of work in the energy sector as well. But primarily it's oil refineries and terminals.
So how do clients traditionally do this work before they were introduced to forged bonding, and how forged bonding solves that? Like what were the traditional methods before this technology?
Well, the primary method, and I would have to say for customers that don't know about it, it's still their primary method, is they take the tank out of service. And that's extremely expensive, especially on the larger tanks. Some of these tanks are, their diameter is larger than the length of a football field. They're massive in size, and it costs millions of dollars to take them out of service. So we've saved quite a few customers from having to take their tanks out of service to perform repairs. There's another older method, which is using polymers to stop leaks. And polymers have their place, and in some situations they work very well. And we fill that gap between where polymers do not work and where they can't get a hot work permit and are forced to take a tank out of service. So that by keeping the tank in service, we save them very large amounts of money.
Right. So, taking the tank out of service is not simply draining it. It's draining it, it's cleaning it, it's degassing it, and it's also the lost production time that tank has in terms of revenue for clients. I mean, there's a lot of economic conditions that make that a very expensive endeavor that ends up effectively being a large capital project, or at least a very big chunk of a maintenance budget, right?
That's right. In fact, some of our customers fail to look at that lost production, or it's hard to quantify because it doesn't fall on the maintenance budget. And
right.
so frequently we're having to show them the real value that we're bringing, which sometimes that lost production is the greatest part of the expense they're going to incur by taking a tank out of service.
Right. What about inside of a process facility where it's not a hundreds of thousands of barrels tank, but you're doing forge bonding inside of a operating refinery? Could be, it's just in the plant. So I guess you're eliminating hot work is a big element of this, in addition to the ability to work on components from a heat treatment standpoint or from a flammability standpoint. How do customers see the elimination of hot work in terms of the value that this brings?
Well, that's huge. First of all, eliminating hot work allows them to do work that they couldn't do before. And second of all, everyone knows that reducing hot work improves safety. And the industry is becoming more and more safety conscious as time moves forward. And so that's what additional value that, again, is hard to put into dollars, but bringing safety to a chemical plant or refinery is huge.
Right.
In the way it's cost.
Yeah, I mean, we do, at Innovator, we do other types of weldless piping connections with our weldless piping, weldless flange services. And what we find is, the cost of hot work, the indirect cost associated with the hot work portion, it isn't actually doing the physical work, is about, anywhere from 5 to 10 times more than the actual work being performed. So, a lot of the time on maintenance budgets, if it's a $5,000 or $10,000 task in terms of the supervision and craft and materials going into actually performing the actual repair, it can be $25,000 to $50,000 or even $100,000 in planning and operators and hot work safety meetings with the entire crew. There's a huge indirect cost that a lot of people who are actually executing the work don't really quantify into the budget. And often that actually becomes part of, it becomes part of overhead, but it's an awful lot of people in an awful lot of meetings doing gas testing and procedures and job hazard analysis and a whole range of things that are not directly seen when you're performing the tasks.
That's right.
And I assume it's the same benefit when you're eliminating that with forge bonding is changing the level of activities that have to happen before the work.
Right. In fact, that's one of the challenges we face when selling our technology to our customers is convincing them to change their standard operating procedure. I guess that's the best way to say it, because they're ingrained. They've been doing this for since the beginning. They have these standard operating procedures, and when there's something that doesn't fit into that, it takes extra work on their end to bring in a new process. And it can happen, but it just takes some time to work your way in. And they love it once they've got it. But it's basically changing the mindset of the industry that they don't necessarily have to take their service lines down in order to repair or install things. We have a chemical plant that we're working on in the Houston area between two of their facilities. And we're installing handrails on over 100 tanks between those two facilities. And they've tried to install these handrails during turnarounds. But what they found is that during a turnaround, everybody's focused on getting the process line back up and running because of the cost of that lost production. And
Right.
so they never have time. They've tried 3 times to install handrails during turnarounds, and they never could get it done. So they called us in, and now we're putting on those handrails on while they're in service.
Right. Because it's not critical task work during the maintenance schedule, so it ends up being tasks that get deferred potentially time and time again as a result.
Right. And they just
Right.
decided we're never going to get these handrails on unless we put them on while it's in service.
Right. Do it during regular production and try to eliminate the hot work and do it during a different cycle, because you don't need the plant shut down to do any type of forged bonding where the applications are right.
Exactly.
Okay. There must have been a lot of research and development and testing gone into forged bonding. Can you kind of walk us through the journey of the kinds of testing and the kinds of R&D that you've had to do over a long period of time to get the technology where you have it today?
Sure. And a lot of that happened in the garage shop of one of our founders and the inventor. And I wasn't
Right.
there for that, but he spent a lot of time and effort developing the bonding process. And then in 2010, when we brought in our first round of funding, we hired an engineer out of NASA, a welding engineer, who could qualify the bond and the stud bond, and put together a procedure for that stud bond. And so that was sort of the beginning of when we had a marketable product, when we could show a welding procedure and a procedural qualification record. So that's required. So that was getting the quality. Then we had the issue of the backside temperature, because everybody's concerned about how much thermal energy is generated in this bonding process and how much of it makes it to the backside of the backside of that piece of metal. When you're bonding the stud on top, how much of it is making it back here? And so we spent a year and a half developing a test and performing the test and taking the data, and then we wrote a paper and we published it with the American Institute of Chemical Engineers. And it shows the means that we took the data, how we took it, our test setup, what the data showed, and then comes to some conclusions. And what we demonstrate is that we have a factor of safety of 2 on that backside temperature. So developing the quality of the weld, there was a great deal of effort put into that, and also making it repeatable so every stud goes down exactly like the other stud. And so we have a forged bonding machine that has a control box that takes the human. It's not an art form like TIG or MIG welding, where you're relying on the skill of a welder. We've set it up so that there's all the technician has to do is prepare the work site and set up the machine, and then it's a matter of a push of a button for him to perform a bond. And so it takes the human error out of it and allows us to put down studs in a very repeatable fashion. That was another part of the development.
It's almost like it's automated forged bonding, right?
Exactly.
You know, in a similar way that people would think about automatic welding versus stick or TIG or MIG. People understand automatic welding is a much more quality bond. It takes the human error element out of the task as much as possible. But your forged bonding equipment effectively eliminates all that. It's a setup and push the button to execute approach to bonding these studs. Correct?
Yes, that's exactly right.
That's fantastic.
Right. Yes. The time is set by a pneumatic timer. And by the way, there's no electricity or electronics involved in our process. It's purely air driven. So you can kind of you can actually say we weld with air. It's a very safe process and very repeatable, very well controlled. It's a controlled energy source, and it allows us to because you might say, well, I don't need any studs today. You know, it's, what am I going to do with that? Well, there's very, very many applications, and our customers keep bringing us new ones. One of the first was to install repair plates on tanks, as you mentioned, the roofs and the tank shells or walls. Well, we can also put plates on the tank bottoms. If you can't get a hot work permit to weld a lap plate on a tank bottom, we can come in and install a lap plate without welding.
Right.
Yeah, I guess getting back to your earlier comment, it's a very highly controlled process.
Right. And you're using it for plates, you're using it for shell sides, like the side of a tank that has corrosion. The tank could be corroding and even potentially leaking. You're doing lap plates. You're doing structural steel effectively with like fall arrest, anchor points, or handrails. What other type? Are you doing stair mounts as well? Is that another application, or am I overstepping there?
No, we have installed stair pedestals for stairs that can be added. We had a tank in Texas that there was crevice corrosion on the well that was attaching the stair tread to the side of the tank, and
Right.
it had corroded all the way through and was leaking naphtha. And so they lowered the level of the naphtha below the defects so that we could work without it leaking. Although we can perform work on the side of a tank if it is leaking, we'll just use polymers as a temporary leak stop, and then we'll work in a clean, a dry area on the outside of the tank while we install our plate. But yes, we had to design a repair that in Texas that would withstand the hydrostatic pressure of the naphtha in that tank when it's full, but also support the OSHA required weight bearing for a stair tread.
Okay. Now, without going or sort of divulging any proprietary things you're developing, where do you see taking the technology with new applications to benefit clients over the coming years?
Well, there's fire suppression that I mentioned earlier, cooling rings on tanks. We have a quote out in the Middle East for installing cooling rings on some tanks at an oil field. And foam fire suppression is another one. And as I mentioned, we've done stairs before. Also, we can hang ladders on sides of tanks. We have a customer that had their stairway corroded. Corrosion is constantly working against you when you're in a chemical plant or refinery. It's all steel, and the weather gets to it. So the stairway was crumbling, and the workers were afraid to walk up the stairs, so they wanted either for us to replace the stairs or to hang ladders. And there's a lot of those situations out in the industry. So we've applied our technology, the forge bonding technology, to an improved method of repairing leaking valves. So it basically replaces drill and tap. So we instead of bonding a stud to a plate, we're bonding an injection fitting to a valve up near the packing gland. And so that's another technology that we have available, and it's safer and far higher quality than drill and tap.
So if you, we do tons and tons of drill and tap leak repair work. If you used a forge bond leak repair injection valve, then that's a high quality bond. It's no longer considered a fugitive emissions leak point. Customers could leave that in service, right? I mean, they wouldn't need to necessarily have to do a more permanent repair or swap that valve out or change that injection valve out like they would with a drill and tap injection valve, as long as depending on the sealant that's used, obviously.
That's right. We do have customers that have told us they're not going to use drill and tap anymore. They're just going to use forge bonding because it allows them to take the valve off their replacement list.
Right.
Okay. Drill and tap valve, you're going to put it on your replacement list because you degraded the asset by performing the drill and tap. With forge bonding, we've actually enhanced the asset because you now have a maintenance platform for re-injecting that valve if it starts leaking again.
Right, and it effectively becomes an integral part of the valve as opposed to a repair component.
Exactly. Yes.
Right.
And yes, our fittings are far stronger than a drill and tap fitting, less likely to break off or leak because when you're drilling and tapping, you only have a few threads holding the injection fitting onto the valve at best. Yes, and then there's a dangerous safety step in the drill and tap process, which we've actually been in discussions with the EPA about including forge bonding as an alternative first attempt for drill and tap on valves for leak stopping of valves.
Depending on the pressure of what you're drilling and tapping into. I mean, you obviously have the safety component while you're drilling just to tap the hole before you even thread in the injection valve. But then you also have the potential exposure once the technician has the injection valve installed and he has to punch through to break, through the last components of that stuffing box to get access into the valve wall to get into the stuffing box. So, often, that requires a high pressure packing gland or some other way to leak components. So, I think there's a whole bunch of ways to make that a more enhanced process. And I think the other thing, depending on how you approach it, is, and you mentioned the EPA and first attempt, there's a whole element of drill and tap when you punch through that you're actually creating a leak point, and releasing some potential emissions before you seal it because of that punch through event, right?
Right, and we actually have a patented injection kit for injecting the valve once we bond the fitting to the valve. It allows us to simultaneously drill and inject at the same time. So the moment we break through that valve bonnet into the packing gland, where the sealant is following it at a slightly higher pressure than what's inside the valve. And then we can back the drill bit out and keep pumping. So we call it a zero emission injection kit. So it does offer an additional advantage over the drill and tap.
Nice. Okay. Let's dive into some frequently asked questions that you often hear from clients as they're looking at, exploring, considering forged bonding. And the first one comes to mind is, how strong are the studs?
Yeah, we do get that question a lot. And so our studs are qualified to ASME Section 9. This is kind of a little mock-up we have that we show customers that we have to pass a bend test, which is what you see here. You have to bend the stud over and straighten it back out without it breaking off. This is a torque test where we put a stack of washers on it and a nut, and then we torque it until something gives. And we only have to pass 8 foot-pounds. It's actually a very easy test. These break off typically about 45 foot-pounds. But notice the bond is not breaking in either one of these. It's the stud breaks off here. And if we take a hydraulic press and we bond the stud and then we pull it, it'll fail at about 5,000 pounds of force. And it actually takes out a piece of the base metal rather than breaking the stud or breaking the bond. So the bond is actually stronger than either of the two metals. So in this case, the base metal actually pulled out of the base metal.
Got it. Okay. How long does it take to bond a stud? Like, what's the length of time?
Well, most of the time is spent during setup, getting onto the tank roof, setting up the equipment. The actual bond itself takes about 3 seconds. That stud is spinning for 3 seconds, and that's it. But you have to then, once you're up and you're set up and running, you have to index your machine from a stud to stud. So that takes a few minutes, and we estimate on a good day, we'll put down 60 studs in a day, depending on the conditions. It can, if we have to work in breathing air, that typically takes longer to close the process down. Yeah, but 60.
So on a handrail, you're talking what, 6 or 8 studs per mount? Is that
usually it's 4 to 6 studs. Yeah, 4 on the roof mount and 6 on the wall mount.
So you could be mounting 8 to 10 brackets a day.
Yeah, sounds about right.
And how about on the plate side of things? If you're on a tank and you've got multiple locations where you need to put down repair plates, what's the typical size of a plate? How many studs are in there? And how many plates can you typically do in a 8 to 10 hour shift?
Right. So the most common size of plate is we call it the 12-bolt plate. We have an 8-bolt plate. We can even do a 4-bolt plate, but we don't put those down very often. In fact, it's probably been, I can count them on one hand as the number we put down of those. But an 8-bolt, 12-bolt plate, and then we put down the largest plate we put down is 8.5 feet by 3.5 feet. So we had 128 studs on that plate. So it varies widely, and that one took us like 2 days just to put the studs down. And then you have to install the plate after that. So the smaller plates, if you're using the 8-bolt plates, you can put half a dozen of those down in a day. And it really, what determines the rate of application is frequently obstructions and, of course, weather delays, working and breathing air. But obstructions can really slow the process down. We commonly, because the rolling ladder on an external floating tank roof is a heavy spot, tends to collect water and chemicals. So there's a lot of failures that occur under that rolling ladder. And so you have to work around that rolling ladder. In some situations, we've actually cut the rolling ladder rail. We've cut a segment out of it so that we could work, and then we reattach it when we're done with bolting.
Okay.
So it's, it's every situation is different. It's rare that, well, maybe half the plates or less than half are out in the open on a tank roof where there's no obstacles. Usually the problems occur where you have complicated weld joints and crevice corrosion creeps in, or like I said, a heavy spot on a roof where the rolling ladder is.
But putting down 4, 6, 8 repair plates, and the plant is, the tank as an example, is in production. So, the impact is minimal because you're not, you don't have a hot work issue. The tank doesn't have to be drained or taken out of service. So whether you're there for 2 days or 8 days putting down repair plates, the comparison in terms of value, in terms of safety, productivity, cost effectiveness for the client is astronomical compared to, the potentially millions of dollars of having to do this traditionally.
Mm-hmm.
Right. So what kinds of materials are we talking about when you're laying down studs and injection valves and those sorts of things? What are you working on, and what are you bonding to?
Most of our work is on carbon steel. Down south, it's A36. Up north, there's a few different varieties of steel they use for the colder weather. So it's typically carbon steel, and our stud is made out of a 304 stainless steel, which is our most, we probably 95 or 98% of the studs we put down is a 5/16 inch 304 stainless steel stud that you see here. It performs a beautiful bond. It's very strong, and we like it. The stainless steel is very immune to the elements as far as corrosion goes, so it makes for a very long-lasting repair. And the plates, they're typically stainless steel, but depending on material compatibility, we might go with a carbon steel. And then just like the tanks are made of different carbon steels, typically we like to use the type of carbon steel that the tank's made of. And then for that plate to seal against the leak, we need to use typically we use a polymer, and then we lay a gasket over the polymer, and the polymer is there to give us a flat surface so that the gasket has a flat surface to seal against. So the polymer fills pits, and it helps us planarize if we're crossing a lap joint, which is very common, and gives that gasket a nice place to seat. And nuts and washers, they're stainless steel, just like the stud.
Okay. And then it's everything is torqued to spec.
That's right. Yeah, torqued in sequence. It's kind of like torquing the bolt pattern on your truck or car. Yeah. We just walk our way around and slowly bring it down.
I mean, effectively, you're creating a gasketed joint and then torquing it to spec. I mean,
That's
no
exactly
different than a
right.
client would with a flange joint, right?
Exactly. That's right.
Okay.
And everything is engineered that we do. We have engineering that backs up every repair, every installation we do to make sure that it's of quality, and it's going to provide the safety if it's a safety device, and it's going to be a long-lasting repair if it's a leak repair.
Right. So what prevents a technician from either over or under bonding the stud?
Well, as we discussed earlier, the machine that performs the bonding eliminates the need to have a highly skilled welder. The machine has a timer on it. There's gauges to monitor pressures and vacuums during the bonding process. So once the machine is set up on the work site, on the work surface, it's a matter of pushing a button, and there's a pneumatic timer that counts down 3 seconds, and when the bond's done, it automatically shuts it off. There's also a redundant timer. Everybody likes redundancy when it comes to safety. So if one timer fails, the other timer is a backup and shuts it off. And there's other safety features that are built into the machine as well.
Okay. Yeah. Again, it just comes back to the language that I hear is automatic stud welding.
Yeah.
right? It's and cold work. um, so customers are thinking about doing this using forged bonding. What does it typically cost to install a repair plate?
Well, when I'm asked that question, I typically give the answer that it's going to cost a lot less than taking that tank out of service. In fact, if it's not a small fraction of that, I'll be surprised. Now, of course, when the tank gets smaller, if you're talking about a 10-foot diameter tank, and it's got a light hydrocarbon in it or something that's easy to wash out, it might be better just to take it out of service and weld it. But once the tanks start getting large, a lot of the tanks we work on are crude oil. They have 3 feet of sludge in the bottom, and this tank is the size of a football field, and taking that out of service is a whole nother ballgame. And that's where our value comes in.
Let's talk about backside temperature when bonding. What is the backside temperature? And I'm sure every customer asks this because they hear friction, they hear forged bonding. Somewhere in there they're going to perceive it as welding. What are we talking about in terms of backside temperatures?
Okay, yeah. So during the bonding process, while the stud is going down, there is thermal energy generated at the top, and during the process, there's a small device that the machine itself is actually covering the stud during the bonding process. You can't see the stud being bonded, and we purge that top side with argon gas during the bonding process. So that guarantees the safety on the top. But it's the backside that everybody's concerned about, because if you're on a floating tank roof, you can't argon purge the backside of that tank. So I'm glad you brought this question up. So the backside temperatures, I'll just say right up front that we exceed the auto ignition temperature of most hydrocarbons that we bond on top of. But due to a fact that is presented in API recommended practice 2216, that if the thermal energy, the thermal footprint that's the hydrocarbon is exposed to is small enough, then it takes a much higher temperature to cause that hydrocarbon to ignite. And the same thing with time. Auto ignition temperature is actually measured over a 10-second interval, a 10-minute interval, 600 seconds. And our bonding process is only 3 seconds, so it's a small fraction of the time duration. And API 2216 also points out that for very short exposure to thermal energy, it takes a much higher temperature to cause ignition. And it's those two factors that we're using in this bonding process to ensure the safety. In fact, the characterization we did and the paper that's the American Institute of Chemical Engineer paper points out and discloses the data that we collected. And it shows that we have a factor of 2 safety margin or greater for I think 11 or 12 hydrocarbons that we've tested to date.
All right. Now you've done a lot of testing with the quality. You've done a lot of testing with the auto ignition circumstances, and you've spent a lot of time with pretty large owner clients who have either accepted or acknowledged this repair as effectively a cold work approved process. So who are some of the owners who have already partaken and take advantage of the technology and approve it?
Well, Shell Oil Company, Valero, Lubrizol, getting ready to start a big project with Dow. There's quite a few big names, Plains All American. There's some of the big players in the game. And they are taking advantage of our technology. I think Phillips 66 is our largest client as far as number of facilities we've worked in. Valero is moving up in the ranks there. I think we've done work in 2 or 3 of their facilities now, but we have a quote out with a 4th one in California, and we're talking to another one in Louisiana. So
okay.
That's, yeah.
Is Exxon taking advantage of this so far?
No, not yet. We've had some dialogue with them, but they aren't using the technology yet.
Okay. Let's talk about how long these plates last.
Well, yeah, that's a good question. We have one customer who, in fact, it's the largest number of plates we put down was on a tank in Louisiana. We put 41 plates down on a tank. It actually was during an API 653 turnaround, which is kind of interesting because most of our work is performed while the tanks are in service. This one was out of service, going through a turnaround, and the tank roof was landed, no product, but they were still picking up traces of benzene, and so they couldn't get a hot work permit to weld on the surface, on the top of the floating roof. And they had blasted the roof; it was already primed, and they found 6 through holes, and there were 35 thinned areas that they wanted plates put over it, but again, they couldn't do it using welding. So they hired us to come in, and we put 41 plates down on the tank roof to bring it back into like new condition. And they are expecting those plates to last for 20 years. And that was back, I believe, in 2015 when we did that.
41 plates.
41 plates.
Was there any of the roof left besides plate?
Yeah, the plates, a lot of them were small plates, but there were various sizes up to about 3 feet on a side.
I remember actually seeing a picture of that, and I think I actually posted it on social media and asked a lot of my connections to guess how many plates were on that picture.
Yeah, that's the one.
Yeah, that's awesome. Is galvanic corrosion an issue?
Galvanic corrosion is not an issue because you do have dissimilar metals. It's a valid concern. But we've talked to corrosion experts, and we've done quite a bit of research on it. It turns out that if the surface area of the stainless steel to the carbon steel that it's attached to is small, if the ratio of the surface areas is small, then galvanic corrosion is not an issue. If we were putting a carbon steel stud on a stainless steel base material or a stainless steel tank, that stud would be gone very quickly. Right. But when it's reversed, there's little to no effect from galvanic corrosion. But the other thing is when we put the plates down, we encapsulate the joint between the tank roof or the tank wall and the stud with the polymer. So the area is void of any electrolytes, and that's one of the 3 components that's necessary for galvanic corrosion. So basically, we've eliminated even though that's not necessary.
Okay. So how much pressure can these repairs sustain?
We've completed a couple months ago. We completed our highest pressure repair at 150 psi. We've done a 99 psi tower. We've done some lower pressures, 60 psi condensate drum, and we have tested it in our shop up to 1,000 psi. On a piece of piping just to demonstrate the amount of pressure we could withstand. And we let it sit for 2 weeks and no issue. We haven't actually performed a work at that pressure, but we know that it's capable of that.
And these are the plate repairs, because obviously if you're doing structural repairs, it's all about its load-bearing capability. What about with your injection valve technology? Have you got any pressure rating or guidelines there?
I don't have a high number on the. We have actually performed a 2,000 psi valve. It was basically a simulation in our shop to find out what the maximum pressure that we could handle was, and we were able to drill and tap a 2,000 psi vessel. But we haven't performed that in the field. I'm not sure the highest pressure we put down in the field.
Okay. On the handrail side, obviously handrails are guided by a variety of safety regulations. What does OSHA have to say about this? I mean, in Canada, it's OH&S, and the regulations are provincial, but you're generally dealing with U.S. OSHA regulations. And how does this comply with that?
Well, OSHA, the general rule, and there's a lot of detailed rules, but the bottom line is if you can withstand 200 pounds of force in any direction on your handrail, then that'll it gets a little more complicated when you have stairs involved. But if you're just on a tank roof with a handrail, it has to withstand 200 psi of force in any direction. And so we use FEA modeling for our engineering primarily. There's some hand calculations, but if you receive an engineering package with Forge Tech's name on it, typically is a finite element analysis result with von Mises stress diagrams and a discussion about it. The older, before FEA analysis was commonplace, typically there were hand calculations used for that were used in the engineering packages. But everything is engineered, even the handrails. We've put together a finite element analysis model of a handrail to prove that it'll withstand those forces.
Okay. I don't know what I haven't looked up what the regulations for handrails are in Canada yet, but I'm going to have to do my homework on that as we start to offer this for clients. But the fact that it's fully engineered and it comes with an FEA package should give every customer confidence that they're going to be getting high quality bonds and meeting their requirements.
Exactly.
Now, this is new technology, and most people are going to be thinking and reading and or listening or watching what we're talking about and trying to get their head around. And most people will have this from a mindset of how they do things today. So, what are some things that customers should be thinking about, asking about this technology, asking about their situation, but are not? They're not really looking at it that way yet. Like what do they need to consider in terms of their mindset around how to utilize forged bonding? What comes to mind to you?
Yeah, well, it's revolves around some of what we talked about earlier. That if they're faced with having to shut down a tank, take it out of service, and it's a moderate to large tank, that's when the value of Forge Tech kicks in. Or if they have, say, a tank wall that needs to be repaired and it's got a liner on it. And there's a lot of tanks that we come across that do have a liner. And sure, if you are welding on the side of a tank 3 feet below the liquid level, it can be safe, but you'll likely burn the liner on the inside of the tank. And now you're just creating a future problem. So our forge bonding process creates very little heat and has very little impact on the liner that's in that tank. So and then we install sensors using these studs that on piping, on high temperature piping, and these sensors are used for monitoring corrosion and erosion of the piping, so they can plan their next outages and find out if their processes are maybe out of balance or something. And so we can bond studs to those pipes without taking the heat treating out of it while the pipes are in service. And I mean, some of these pipes are 700 degrees Fahrenheit while we're working on them, and it actually shortens our bonding cycle. We will actually characterize our bond based on the temperature of the base material, because it's like a preheat, and the metal is up hot before we start bonding. So that 3-second bond can come down to 1.5 seconds if we're bonding on a 600 or 700 degree Fahrenheit pipe.
So they've really got to think about the whole value of how this eliminates a bunch of different problems. It's not just about connecting a stud to whatever material. It's the value of being able to work on piping or work on tanks that they couldn't normally with any traditional method, or they've got to look at it from the point of view of how it could eliminate doing this kind of work during a shutdown in a process plant, or having a shutdown and take an entire storage tank out of service. So there's we often have these conversations with clients on weldless piping applications, when, depending on who you're talking to, they're comparing, the cost of doing the welding versus the cost of the weldless piping connection, and you really got to have a broader conversation on the whole value and what the cost is all the costs that you're eliminating out of that spend cycle, particularly all the complications with hot work.
That's exactly right. As I mentioned earlier, oftentimes the greatest value is keeping the process line up and running. It's because we get compared to welding all the time. Well, why don't you just weld the plate? Well, yeah, if you can weld it, I actually say you probably should, because it takes us a lot longer to put a plate down than a welder can put a plate down.
Right. Yeah. If they can weld it and it doesn't have a whole bunch of other complications, then if that's a viable option, then that's what they should do.
Right. Exactly.
Right. So, can studs be bonded to steel without taking the heat treatment out then?
That's correct. Yes. And there is, it's an extremely shallow heat affected zone. It doesn't penetrate the entire pipe, at least on the pipes that we've looked at. And we've had 30 third parties analyze our bond on various piping material. And there is some very small amount of hardening that goes on right at the surface where the bond takes place, but it's minimal. On carbon steel, there's almost no hardening at all. And on like 5 and 9 chrome, there's a small amount of hardening, but it's very shallow and it doesn't penetrate the entire pipe.
Okay. You've been working on this for almost 10 years now, or 10 years, going into your 10th year. What are the biggest obstacles you're facing with selling this technology and getting client adoption?
Right. It's getting them to step outside of their standard operating procedure. They have their way of doing things, and they've been doing it forevermore since the beginning. The younger engineers tend to adopt our technology and are more receptive to it than the ones that have been there for a while. I guess they're a little more open-minded to the new technologies. They grew up with them. Most of us grew up without much technology in our lives, and so it's sometimes a little bit more difficult to us to see the value of it. But the younger engineers really love the forge bonding technology because it gives them something new to work with.
Yeah, the millennial generation tend to be, they tend to be innovators. They grew up with technology, so they're always looking for different. My company's called Innovator, but I'm Generation X, and I grew up. I remember growing up on refinery shutdowns where it was still hammer wrenches and the rattling of impacts, and so there's a lot of changes happen in my last 27 years, and but I think adoption of new technology in our space is I think the industrial space tends to be a bit of a laggard in terms of adopting technology, but hopefully the younger technical types are going to increase that velocity and hopefully accelerate it.
Exactly. Yeah.
Who do you typically need to get to, like with your clients? Like at what level to create that sort of that management of change thinking?
Well, usually what we find is that it's an inner circle, and every company, every terminal works different. Every refinery, every terminal, every chemical plant. There's usually a group of people that have to all approve the technology. You've got safety, you've got inspection, engineering, and then management, maintenance. They all need to approve it and buy in because most of the managers who have the ultimate decision want buy-in from all of the people that are involved. So It's usually, we call it an inner circle that we need to get to. And in terminals or facilities that aren't heavily staffed, it could be one person, but usually it's a couple. At a very dense refinery, it might be a dozen people we have to prove ourselves to.
Are you often having to sort of actually step outside of the terminal or the facility and get with the technical authority back at their head office if they've got a technical authority engineering office elsewhere? Do you spend much time having to work with them to get them on board as well?
That's a good question. Some facilities operate from top down. In other words, all the decisions on how they're going to make repairs, for example, are dictated out of a corporate office. And so you do have to get to those people in the corporate office who make those decisions. And then others, they're allowed to work more autonomously, where they allow each facility, and each one might do it differently. And then you have to go to each facility and sell them on the idea. So different depending on the customer. But you're right. A lot of times you're going to corporate headquarters to have it.
Yeah, we find with new technology, we kind of got to do both. We have to get some good buy-in and sponsorship with a variety of technical stakeholders at the site level who have some particular applications, And then there's generally a chief inspector and an engineering support team back at head office who maybe own their operating standards, who either need to sanction this new approach, give it a deviation, and then maybe even eventually adopt it and roll it into their new standard operating practices. And I think that's true for larger companies that have multiple facilities, that they do have a central technical team that might be the owners of their standard operating practices.
Yeah, that's right.
So on the installation side, you've overcome those technical approvals. You've gotten people to understand the value. You're now in the field. You're executing that work. What are the typical obstacles you're seeing during installation?
Obstructions are probably the biggest problem that we have to work around. And actually, here's another one. We're usually, or it's not uncommon for us to be a second or third attempt. Okay, so if we would have been the first, we'd have a nice smooth surface to work on, but by the time we get out there,
repairing over top of a repair on top of a repair.
Exactly. So now we're dealing with an anthill with polymers or some kind of contraption, wooden plugs that they've hammered into the holes, or screws with washers on them, and so now we're having to work over or around these things. And most of our customers, and we're more comfortable with it. Most of our customers say, we don't want you to take off what's already there. You just need to fix it. Add another thing to it. So sometimes we're putting a much larger and more expensive enclosure over this. What's already been done. We have some extreme examples of that. That it's actually in our presentation. It's amazing what we come across. But if we're the first ones out there, we can put a nice temporary leak stop in the hole just to, that will allow us to work in a clean area. We'll put a flat plate over it. It'll be quick and easy. And so we encourage our customers to call us on the first attempt rather than wait till they've made several attempts and spent a lot of money that didn't get them anywhere.
I think it's no different than a lot of on-stream leak repair where, the maintenance team might try to put a rubber patch on it with some banding, and then they get, some sort of plumber's clamp, like a robar clamp, and then that's what's holding back some sort of a high pressure pinhole leak. But those clamps are not really stopping the leak; they're just diverting it everywhere, and it might have been the good Band-Aid for the day or two, but it actually makes the more permanent repair a little more complicated and likely a lot more expensive, because you now, instead of laying down a straight plate, you're probably building some sort of a top hat to go over top of other obstructions.
Exactly.
Right. So let's talk about certification. How are forged bonded studs certified?
They're ASME section unqualified, so they do comply and they pass with flying colors. As I mentioned, the studs only need to handle 8 foot-pounds of torque, and they don't fail until 45 foot-pounds. And the bending, actually that's what I was showing earlier here. The bending is another test that you have to perform. So really, the bend and torque is all you have to pass. It's fairly straightforward. If you're involved with, if our stud bonding is between materials that are not P1 materials, I think P1 to P8, then you have to do a microscopic examination by cutting the stud in half and looking at it under a microscope after etching it. And so we do that when we start working with exotic metals. We just qualified an A20 stainless steel stud onto a 2205 duplex tank, and we performed a repair in the Houston area recently with that. So, and anytime we're thrown with a new material that we haven't qualified, we have to go through the qualification process, which can take a week or two, if depending on availability of engineers to work on it. But if it's not carbon steel that we're working with, we have to perform this cross section of the stud.
Okay. Now you mentioned that all of your repairs are engineered FEA. You're typically giving your clients an engineering package. So on the material side, be pretty standard on the plates and on the studs that you either do or can supply MTRs on the materials?
Yes, that's
Yeah.
usually the customer requests that we provide those with the engineering package.
Right. So if all the materials have full traceability.
Correct, and the SDS is for the polymers that we use in the gasket material.
Right. Okay. What about API standards? How does your solution meet compliance with that?
Well, API 653 is typically what we fall under, since this is a repair. That most of our work is a repair or in making a modification to a tank. And actually, we are on API's agenda. I presented at the spring meeting this past May, and so forge bonding is now on the API agenda for consideration to be put into the standard. And so there's a small working group that's been assembled. I believe there's 6 or 7 people on it, and we're going to figure out where. In fact, I'm working on that right now. Figure out where in the standard it would best fit. And then we're going to come up with language and then have that brought to the committee to figure out, if that's the best place to put it. So, so we are working on being included in the standard. It was very well received this last meeting, and so I'm excited about it that we're going to be moving forward on it. They said it's probably going to take a year or two. Well, actually, more like a year to 3 years is what they're saying. They said this one is more straightforward than some of the ones we've included recently, and they said it's probably 2 years is reasonable. But as far as compliance with API 653 right now, in the front side of, I think it's the second page or third page of API, there's a paragraph in there that discusses this, and that is that API was designed so that you don't have to engineer everything you do to a tank. And so if you follow the standard, you can avoid having to engineer it, and it saves a lot of time and money, and it becomes kind of standard practice.
Right.
However, it says that the standard is not intended to prevent you from doing other things. And as long as you use good engineering judgment, that there's no reason you can't do other things to the tank. And so we fall into that category right now.
Right.
We engineer all of our
It's much like on the ASME side, where you've got the post-construction codes that give you guidelines and recommendations for repairs and modifications that are not always explicitly detailed.
Exactly. Yes.
Right. Okay. Now, just for the Canadian audience, a couple of years ago, we worked with you and actually had your well procedure registered here in Alberta with the Alberta Boiler Safety Association. So your WPS is actually registered in Canada, is it not?
That's correct. Yes.
Right. Why not wait? Why not wait until the next turnaround to install? Why shouldn't clients wait until the next turnaround to install anchor points, fall protection, fire suppression systems? Like, why do it when it's on the fly? When it's running?
Well, it's all about taking that unit down. That's the so forge bonding allows our customers to upgrade their safety, to enhance safety for their employees, their workers, the vendors that they bring in routinely to do work. They can upgrade it now without having to wait for the next turnaround or shutting down their process lines and spending the money, losing the opportunity there.
Right. I know it's also, the kinds of repairs that we would do with forge bonding can often get on the turnaround exceptions list when schedule or something, when scope starts getting cut in the middle of a turnaround. So there's a risk that they put it on the turnaround list and it gets cut. And so, you don't have to put this stuff on the turnaround list.
Right. And that's what was happening at that chemical company in the Houston area. It made 3 attempts and it kept getting cut, and they actually were able to weld a few handrail brackets on, but that was it. And they said, we're just never going to get this done. And they're tired of waiting to improve safety for their workers. That's just the bottom line.
Right. So, if we're a pipeline company, terminal company, refinery, upgrader, chemical plant, all these large industrial facilities have some version of tankage and pressurized piping. How will this help them become more competitive?
Well, certainly by saving them the expense of taking their process lines down, fewer interruptions. That's It's not uncommon for us to receive notice that the customer is on a 45-day notice from EPA because they've got a leak and they've got 45 days to address it. And so it's fairly urgent, but that 45 days is very comfortable for us to perform the engineering work if there's any that needs to be done for that particular job. And by the way, we do have standard repair plates. We've engineered them in the past, and so if we can reuse what we already have, then that's good for everybody.
Allows you to scale and respond quickly with sort of standard templates, because you've got templates that match up with plates to allow for that standardization, right?
That's exactly right. That 8 and 12 bolt patterned plate is our bread and butter, and we put a lot of those down just standard.
And you've got the jigs for the installation of those plates already prepared to match up with standard plate applications.
That's correct. Right. It's more than just designing the plate. There's actually our primary means of securing our equipment to a tank roof. Let's take, for example, is a vacuum clamp. So we have a plate and it gets pulled against the tank roof of the vacuum because we're applying a substantial force more than a couple of technicians can hold down. They can't hold this machine against the tank roof. So it's in excess of 1,000 pounds that we're applying to that stud. So we have a vacuum clamp. I'm sorry.
I remember playing around with it in your shop a few years ago, and I was impressed with the strength of your vacuum clamping system in terms of how much force it would take. It's quite an impressive design.
Yeah, it's amazing how much force you can get out of a vacuum clamp. So, but we have to design that vacuum clamp for each plate or enclosure that we put down because there's a hole pattern that's predefined and machined into that vacuum clamp, and it's the locations where each stud's going to go. So the vacuum clamp's actually acting as the template for our stud pattern.
Right. Yeah. So it's like a jig.
Yes, exactly.
Yeah.
It's a jig.
Awesome.
Yeah. Mm-hmm.
So you mentioned this before, but clients have a liner inside of their tank that might be damaged if they weld on it, but you can repair that and not damage the liner. Just sort of talk about that a little bit in terms, and how are you accomplishing that and why?
Well, if they, the liner's there for a reason to limit the corrosion. Sometimes the process in the tank will work its way from the inside of the tank out, and the liner's there to protect that. So if you weld on the tank, it's gonna destroy the liner, and now the product gets to the steel, and it's gonna create it's not a defect right then, but sometime in the near future that can work its way through the tank and create a new defect. So the amount of thermal energy, which by the way, on the back side of that plate, that I was showing you here, the back side here is about 1.2 BTUs of thermal energy, very, very small amount of heat. And it's very short-lived as well. It's there for a few seconds. So and on a tank wall tends to be thicker too. If they're at the bottom of a tank, you might be talking an inch thick, and there's really no significant heat that makes it through on a piece of steel that thick. It's a tank roof, which is what this is actually equivalent to a tank roof. It's a 3/16 inch thick, and that's the thickness that we performed all of our backside temperature measurements on. Once you get thicker, the temperature drops off dramatically. But on a 3/16 inch plate, that thermal energy is 1.2 BTUs, which, by the way, that's the amount of thermal energy it takes to heat. 1 BTU is the amount of thermal energy it takes to heat 1 cup of water by 1 degree Celsius. So it's really a very small amount of energy that's produced.
Very small amount of energy, absolutely. You couldn't make a cup of coffee with it.
Yeah, exactly. You could not make a cup of coffee. So yeah, and so the liner stays intact, and the process in the tank doesn't attack the steel.
Just to kind of conclude our conversation, I'm an owner of a facility, whether that's refinery, chemical, storage terminal. What do you recommend in terms of when should they consider forged bonding?
It's if they're facing if they can't get a hot work permit and they're looking at taking their tank out of service or shutting their process line down, If they have a liner on the tank and they don't want to damage it with welding, those are two good examples. Another good example, I'll kind of use a case study. We had a 5-foot diameter condensate drum. And you might say, well, 5 feet, I can just put a traditional leak sealing clamp around that. But turns out on pressure vessels, in fact, I'll make 2 points here about pressure vessels. But once that pressure vessel may have been made round, but by the time it's been put into service and pressurized up, it's not round anymore. In fact, nothing we work on is round or flat. Tank roofs are not flat and the walls are not round. There's flat spots in them. There's humps in them. It's amazing how irregular the surfaces are that we work on, and we adapt to those surfaces. But so because that pressure vessel is not round, it's difficult. You would never be able to put a 5-foot clamp around that. Not to mention that's going to be probably prohibitively expensive, and there's frequently obstacles in the way to installing a clamp that size. And if you could get the clamp around it, you're not going to get a good seal because the clamp is going to be machined round, but the pressure vessel is not round anymore. The other thing is we talked to, this is a little different subject, but it relates to pressure vessels. And we spoke with a licensed inspector for pressure vessels. And he said, forged bonding does not disrupt the pressure membrane, and therefore it would not void the R stamp on a pressure vessel. So that's another advantage. If you weld on a pressure vessel, you're going to avoid the R stamp. And an owner of that tank can do that if they want, but it's at their own risk.
Right.
So that's another big advantage.
I think that's a huge selling point. That I mean, you know, pretty difficult to get a client, an owner, to weld on a pressure vessel. And if they do, it's a pretty significant. It tends to be a big, a critical path project on a major turnaround where there's an awful lot of work to be done, including an army of heat treatment people to deal with the aftermath.
Right.
Great. I think that about wraps it up, Matt. Do you have any kind of closing comments?
Well, I think I'm excited about this technology. It's bringing tremendous value to the industry. And we have customers who routinely are high-fiving our technicians because we just saved them $500,000 or $2 million from not having to take their tank out of service. So, and we're gaining traction, and we're just looking forward to spreading this on a much broader sales footprint. In fact, it's one reason we've started to license our technology recently is we're trying to expand our market more quickly through our licensees. We're located in Houston, and we're handling the Gulf Coast, but once we start to travel, it becomes more difficult. So we're handing those jobs off to our licensees.
Man, we could have saved ourselves an hour and a half if you just had told me. Just tell customers they're going to high five us every time we save them $500,000 to $2 million, and let's wrap it up. Because I think that's the the devil's in the details, but that's the real benefit. Is this technology safe? This technology is designed to eliminate a ton of things that cost money and downtime and lost production. Ultimately, safer, more cost effective, and driving customer productivity. Right? I mean, that's it. In terms of innovators' goals around innovation, that's the trifecta that we look for. How do we improve our customer safety? How do we improve our customers' cost effectiveness? How do we improve their productivity? And I think forged bonding checks all those boxes in spades.
It really does. It does. And we stand behind everything we do. So we look forward to helping you push this out into the market in Canada. I think it's
we're excited about it. I'm looking forward to it. And we've recently had Mike up here, and a whole team of our technicians have now been certified to your process. So we are ready to go to bring this to customers in Canada. And and I guess this is the inaugural announcement to all of our clients across the country that forged bonding is available and north of the 49th.
And there you have it, though that doesn't have to be the end. If you haven't already, please give us a follow wherever you find your podcast, and don't forget to check out both our host Don Cooper and his company, Innovator, as well as our guest by following the links in the description.